Hi everyone, I'm Tuan, a lecturer at the University of Melbourne. Today I'm going to present my work in collaboration with Marcel from Monash University and Abik from the National University of Singapore. In this work, we design and build AFLNet, a Greybox Fuzzer for network protocols. To the best of my knowledge, this is the first Greybox Fuzzer that combines code coverage feedback and state feedback, makes them work hand in hand together to tackle challenges of fuzzing stateful network protocols. First, let me explain the motivation behind our work. I think we all know that network protocols are important because these enable many services that we are using every day at work, at home, and even when we are traveling. For instance, the RTSP protocol enables video streaming services, and the OPC UA protocol allows machines to talk to each other in an industrial network. Since these network services are widely used, any security flaw in this protocol implementation could lead to severe impact. So the protocol implementations, such as network servers, should be tested carefully to prevent attackers from compromising the system, and fuzzing is a viable approach. The idea of fuzzing is pretty simple. It generates and sends a huge number of inputs, including valid and invalid inputs to the system under test in order to trigger abnormal behaviors like system crash. Depend on how much information the fuzzer knows about the system under test, we have basically three types of fuzzing, including black box fuzzing, gray box fuzzing, and white box fuzzing. This diagram is for coverage-guided Greybox fuzzing, which is considered the most effective and common fuzzing approach nowadays. In this diagram, the fuzzer sends an input to the system under test, and through a feedback channel, it monitors the code coverage achieved by the input, and it will retain those inputs that can trigger new interesting behavior like covering new branches on the control flow graph. Those inputs will be used to generate next generations of inputs, and the whole process keep running until the fuzzer is terminated. However, fuzzing protocol implementation is challenging. The main reason is that many protocols are stateful, so the server under test accepts sequence of messages instead of a single message like in the previous diagram. And its behavior depends not only on the current message but also on the current program state that is controlled by previous message. Therefore, the message order and the state information are important. On the right hand side, you see a sample FTP section in which a FTP client tries to log into the server and upload a file to a folder. The messages sent from the client are highlighted in red, and the messages sent from the server are in black color. In order to create a folder, the client needs to drive the server into a state at which the authentication has been successful. Otherwise, the server will continuously ask for correct username and password. The popular corporate Greybox Fuzzer like AFL cannot handle these challenges. In fact, many AFL users are aware of this limitation, and they have requested the stateful fuzzing feature added to the tool. Here are two of those requests. In the first request, Paul said that one of the things that I struggle with is the limitation of AFL seems to have in that it only performs fuzzing with one input or file. For many systems such as network protocols, it would be useful if fuzzing could be done on a sequence of inputs. This sequence of inputs might be, for example, messages necessary to complete a handshake TLS protocol. To tackle these challenges, we designed and implemented AFLNet, the first Greybox Fuzzer for stateful network protocols. From a high-level view, AFLNet takes a mutational approach and uses state feedback to dynamically construct a protocol state machine and guide the fuzzing process together with code coverage feedback. So because we take the mutational approach, we can leverage all the real-world traffic between the actual client and the actual server of a specific protocol as the seed input, and we build the corpus, we use the corpus, and we mutate the input in the corpus in order to generate another variation of the message sequence and send them to the server under test. At the same time, the server under test is monitored including the code couplets and also the responses in order to construct the state machine. And the state machine is used to guide the whole fuzzing process. So we have a closed loop here. I will explain how each component works in a minute. Before that, I will talk about the state machine learning component, one of the key components that enable the effectiveness and efficiency of AFLNet. We decided to build an automatic and dynamic state machine inferencing algorithm for AFLNet. Compared to a manually crafted state machine, our approach has several advantages. First, it is not time consuming. Without our approach, someone with required domain knowledge would need to spend lots of time to read the protocol specification, which is normally very long and complicated. Moreover, the implemented protocol could be different from the one explained in the specification. For instance, this is the state machine of Type 555, a widely used RTSP protocol implementation. In this implementation, the developer handled one command differently, leading to an undocumented transition highlighted in red here. And AFLNet can exactly capture the implemented protocol. I'm using the same FTP example before to explain how AFLNet dynamically constructs the state machine of the server under test. A state machine is a graph in which nodes represent the program state, and the transition, the axis show the transition between the states. AFLNet uses the server response code as the state identification. As you see, for each server responses, we have the first number here as the response code, which shows the current state of the server. You can see that the response code and their order on the left hand side here are captured very well on the right hand side in the state machine. And AFLNet can automatically generate more message sequences from the sample sections, and the state machine will be dynamically populated. More nodes will be added, more transition will be added. AFLNet leverages the dynamically constructed state machine to drive its exploration. Specifically, it prioritizes the progressive states that contribute more toward increased code coverage, and it's basically work in four steps. First, it selects a target state that is more progressive. Second, it selects a sequence of messages that can reach the target state. Third, it mutates the selected message sequence to generate thousands of its variations and send them to the server under test. For each newly generated message sequence sent to the server under test, the code coverage and the server responses are monitored to decide whether the message sequence should be retained or the state machine should be updated. As a concrete example, suppose that we have an original message sequence extracted from the sample FTP sections. The sequence traverses the black and the black state and the black transition on the state machine here. And then AFLNet identifies the state 331 as a progressive state. It will generate a variation of the original message sequence in which the password is mutated and become invalid. When the new message sequence is sent to the server, it covers new code and new state, so it will be retained. And for further fuzzing route, it will be mutated. And the state machine will be updated. We can see the new node is added and also new transitions are added here. We evaluated AFLNet on two popular protocols, FTP and RTSP, in comparison with AFL and BlueFuzz, a black box stateful fuzzer. The results show that AFLNet outperforms BlueFuzz and AFL in all important coverage metrics, and the number of bugs found. AFLNet found 4 vulnerabilities in the Live 555 RTSP server, and 2 of them are 0-day. The vulnerabilities could lead to attacks like remote code execution on devices like webcam and smart TV. One CV is attributed directly to AFLNet's capability of doing stateful fuzzing. In this case, AFLNet managed to discover a new state transition as highlighted in red here, retain the message sequence, and do stress testing on that target state to trigger a use after free error. This kind of stateful bug is important and challenging to find. Let's read this comment from an AFL user. He said that I'm using AFL 2.5 package update for 3 years, but never managed to detect stateful bug with this. We released AFLNet on GitHub in March this year, and the tool keeps evolving. From only 2 protocols in 7 months, it now supports 8 protocols in total, in which 3 protocols are contributed by AFLNet users, and I'm aware of many other protocols under development. AFLNet normally finds many zero vulnerabilities in the newly added protocols. The GitHub repository has received more than 300 stars already, which is a pretty high number of stars compared to similar projects. We are also working on several improvements for the tools. As the tool is available freely on GitHub and it is very easy to set up, please give it a try. Thank you for listening to my talk.